This is section 3 of our Unit 8 Ecology notes, and today we are going to be talking about population ecology. So population ecology deals with understanding the factors that drive changes in population size. Population ecology provides us with insights into the factors that promote population growth, as well as factors that will limit the population growth. These factors are relevant to all organisms, including humans. So, populations obviously have particular characteristics like size and density. So population size deals with the number of individuals in a given area, and population density is the number of individuals in a given area divided by the size of that area. So when we're talking about density, we're calculating and determining whether a population is densely crowded or relatively scarce compared to other populations. So are they packed into a certain area, or are they more spread out? So when we're dealing with population range and distribution, geographic range of the population is the area over which a population is spread. So geographic range is determined by where there are favorable conditions for a species to live and whether individuals can get to that area with the favorable conditions. Population distribution is a measure of how clumped individuals are within that geographic range. So we could see a random distribution where there is no pattern, uniform distribution where individuals are evenly spaced, or a clumped distribution where individuals aggregate together, often in response to clumped distributions of food, or where there are benefits of social behavior together. We could also see population sex ratios and age structures. So when we're talking about the sex ratio, we're talking about the ratio of males to females within a population. So in some species, the ratio can be different, although it's typically 50-50. Sex ratios can have a large impact on the number of offspring that can be produced by a population. When we're looking at age structure, we're looking at the number of individuals in different age categories. So the different number of individuals in different age categories can have a large effect on the number of offspring produced by populations each year, depending on the age structure, depends on how many individuals are within that offspring producing stage of life. So when we see changes in population size, we see in humans, we often want to predict future population sizes to determine whether the world can continue to support the growing human population, which, as we know, we are growing exponentially. And ecologists want to understand the increases and decreases in plant and animal populations to help protect them from going extinct. So at the most fundamental level, we essentially will see that if the birth rate is greater than the death rate, population sizes increase, and if the birth rate is less than the death rate, the population will decrease. So births and deaths. The movement of individuals into a population, immigration, and out of a population, which is called emigration, can also be important factors in population change. So birth rate and death rate, and then immigration and emigration. So when we're looking at changes in population size, obviously, this can be represented mathematically. So here we go with some math, guys. So N is going to equal our population size. dN will be like delta N, the change in the population size, and dt is going to equal the change in time. So therefore, if we do the change in the population size divided by the change in time, that will indicate the rate of change in population size over time. So to determine the rate of change in a population size, we can identify population sizes at different points in time. So the N at the population size at 0 is the population size at time 0, and then time passes, and we could see N1. So that would be the population size at that first time that we're really checking in. So typically, here we would see that the change in the population size over the change in time is equal to N1 minus N0. So how population changes in size over time. So we can use this with birth and death rates for a given year. So we want to do the change in population size over the change in time. That should be equal to births minus deaths. So for example, if we had 20 births in a population that year and 10 deaths, we would do the change in population, okay, and over the change in time. So 20 minus 10, we have that, so 20 births minus 10 deaths. So that would equal 10 individuals added to our population in that year. So essentially, we can calculate the change in population over time, but it can be difficult to determine whether an increase in population or a decrease in population is substantial or is it trivial. We really need to know the size of the initial population. So if a population starts with 10 individuals and grows by 10 individuals in a year, it's increased by 100% and is therefore growing rapidly. But if you think about it, if we're talking about a population that starts with 1,000 individuals and it grows by 10 individuals in a year, then the population is only increased by 1%. So that's a big difference on those two situations. So we really do need to know the size of the starting population. So to give us a sense of how much a population is growing, we need to assess the growth of the population relative to the initial size of the population. So that is called calculating the per capita growth rate, which we will represent with the letter R. And that is the rate of population change divided by the size of the population. So we've got that population change divided by the size of that initial population. So the per capita growth rate allows us to assess how rapidly a population is expected to increase or decrease over time. When R is a positive number, the population increases, and when it's a negative number, it would be decreasing. So when those numbers are large, we will see it in a rapid increase or a rapid decrease. So here is an example. Here's the two examples that I gave earlier. So we've got the change in population over time is 10 individuals in a year. So when we said the original population had 10, so we had 10 individuals, we added 10 individuals. So 10 divided by 10 is 1, okay? And that represents a big, 1 is a big number, so we would see a lot of change. That's a positive increase in individuals. And then here, our other example, so we had 10 individuals born that year. If the original size of the population is 1,000, then we've got 10 divided by 1,000, so our per capita growth rate would be 0.01, which is not a large number. We're still seeing an increase, but it's not a rapid increase. If R were to equal 0, the population is stable because the birth and death rates would be equal, and we don't see a change in size over time. So most often, every environment has some sort of restrictions on a population. Organisms don't typically grow, populations don't typically grow unchecked, right? So essentially, we would see this exponential growth model if there were no constraints on a population. We would see exponential growth. So here we can predict the change in population size per unit of time based on the current population size and the maximum per capita growth rate. The maximum per capita growth rate is the growth rate when the population is living without any constraints. So we will use R max for the maximum per capita growth rate. So because we assume no constraints on growth in this exponential growth model, when we don't have any constraints, so this is just, obviously this isn't typically how it goes, but if there, sometimes we don't see constraints on a population, we assume no constraints on growth, the population will grow faster whenever it has an increase in the maximum per capita growth rate or a large number of individuals that are reproducing. Okay, so here we see the change in population over change in time is the R max N. So for this, if we tell you that the R max is 0.4, okay, and the original population was 10, then the change in population over time would equal the R max times the n, our original population number. So 0.4 times 10 in this particular case, then the change in population over time is 4 individuals over that year. Okay, so this means that when the population has 10 individuals, we will add 4 more individuals during the next time step. Okay, so let's look at another example. If the population is much larger, let's look at an individual population that's 80 individuals. The rate of population increases will be 8 times larger. So we would add 32 individuals, which causes the J-shaped curve to rise much more quickly. So we would see the change in population over time, R max n for our exponential growth model. So 0.4 times 80. So the change in population over time would be 32 individuals. So this is an excellent starting point for understanding how populations grow over time, but we know that real populations in nature that exhibit exponential growth, there are real populations that do this, but a population cannot experience indefinite growth because they are limited by a food supply or some other constraint. So here we have survivorship curves. When we examine the probability of species surviving over their lifetime, they generally follow one of 3 patterns. Either we see individuals that experience high survival throughout most of their life, and then they decline as life goes on. So humans, we typically see humans having an average lifespan of 78 years. Type 2 individuals, typically like small mammals and birds, they tend to lose numbers steadily throughout their lives. And then we see type 3 individuals, which we experience early life mortality, and then that kind of levels out, and then they die at an older age. So insects, amphibians, many small species of plants. So we have K and R selected species. K-selected species follow the carrying capacity of the environment. They tend to hover around carrying capacity, and their populations typically remain pretty stable based on what the environment can sustain. Okay. R-selected organisms, so they commonly exhibit type 3 survivorship curves. So you'll see that they produce a lot of organisms at once, and you'll see them dying off. So here's a video to kind of explain that a little more if you need that. So that is our lesson for today. We will be revisiting our math very shortly, so don't forget about it.